All right, and coming up next, we have Matthew Kuhns. Matthew, are you on the line?
Yes, I am.
And how am I doing with your last name? Did I pronounce that correctly?
Yeah, I think so.
Wonderful. Let me know when you're ready. I don't have much of an introduction for you, so you may want to take 20 seconds and do an introduction on your own, but you let me know and we'll get it over to you when you're ready.
Sounds good. I'm ready.
All right then. Matthew Kuhns is Chief Engineer of Masten Space Systems, and please welcome him.
All right, thank you very much. Glad to be here today. Let's see, is my video working? I can't tell.
It is, yes. We have sort of an up-angled shot to your
Do you
collar.
see me?
Yeah, that's much better. Yes.
Okay.
The exposure kicked in. We can see the Saturn V in the background.
Perfect. All right, we'll roll with that then. So, well, good morning, everyone, or good afternoon. From Masten Space Systems, we're a small company located in Mojave at the Mojave Air and Spaceport, and I'm just going to talk today about some of the exciting things that we are doing, a broad overview of a number of our lunar and propulsion programs. Right, next slide. So to give you a little history of Masten, the company started back in 2004 and then evolved once by winning the NASA Centennial Challenge Northrop Grumman Lunar Lander X Prize, which is a hell of a title, back in 2009 with the Zombie and the Zoe landers. Since then, Masten's built 5 rocket-powered landers and flown over 600 flights up in the Mojave Desert. So we're transportation focused, and we would like to create and support cislunar economy together with other space companies, and basically create a way we can live, work, and stay on the moon and other planets, as well as laying the groundwork for future manned exploration through the Artemis program and developing exciting new technologies along the way. So the latest news from the company is NASA just awarded us through the CLIPS program. They're the anchor customer for landing XL1 on the lunar South Pole in late 2022. Next slide. And this is XL1, our lunar lander. So the Commercial Lunar Payload Services Program, abbreviated CLIPS, it's kind of like if you're familiar with it, the Commercial Cargo Transport Program to the ISS, only this one is going to the moon, kind of as a precursor missions and support missions for the Artemis program. So Masten has been working on XL1 for the last 5 years. Much of that time in partnership with NASA, Marshall Space Flight Center, and JSC through the Catalyst program. And this lander just builds on all of the lessons learned from the hundreds of flights on our other rocket-powered vehicles. And so we're using all of the terrestrial technology as a risk reduction and testbed platform as we go towards the moon. So for terrestrial testing, we actually do have a XL1T. We need to work on these names. But that T is for terrestrial, and that's where we'll be doing hardware risk reduction, particularly on propulsion systems and GNC. And I didn't put videos in here because I wasn't sure how they would play over Zoom, but Scott Manley just showed some clips just a couple weeks ago about, and you can see XL1T flying a hardware in the loop demonstration for our GNC system, and that was done in partnership with JSC and the Catalyst program last year. So planning to launch in late 2022, and we're excited for all the work between now and then because we're building a spaceship. Next slide. And this is XL1T for our terrestrial risk reduction. It's going to enable us to test the propulsion system, guidance, navigation, and control, the electrical systems, and payload integration here in a controlled terrestrial environment so we can rapidly iterate through test. That's really a benchmark of what we do at Masten. We try to get out into the field fast so we can iterate in a safe environment. And we do that through tether testing. So we put the vehicles hanging from a tether, and so that if something does go wrong, you shut down the vehicle, nothing gets damaged, you can go back to the shop, fix it, and then be out as soon as the next day testing the next iteration. You'll notice the design has evolved a little bit from the T version shown here and the version we're sending to the moon, but the test bed still provides enough relevant data to be extraordinarily useful. And then on the right, you see some of our main engine testing from our green hypergalls. So we really like the green hypergalls because I personally don't like working with extremely toxic propellants, and the rest of the team doesn't either. So this keeps everybody safer, and we get about the same performance out of it. So all of that testing is kicking into high gear now, and should be some more stuff in the coming months. Next slide. So here you see some more pictures of testing, the green hypergalls on the left, and then a render of one of the lunar engine concepts on the right, the vacuum nozzle. So these propellants are safer and simpler to handle than the toxic ones. And then another key portion is our engines are deep throttling, just like our engines here on our terrestrial vehicles, so that we can do safe, controlled, precision landing on the moon. Next slide. So as part of all of this spool up, and what we've been doing for the last 10 years is Earth-based risk reduction under the NASA Flight Opportunities Program for commercial customers as well as government customers. This is a picture of our Zodiac vertical takeoff, vertical landing rocket in Mojave, and that's the little white thing on the upper right side of the rocket is the NASA Splice payload. That is a vision system that will be used on future lunar landings. So we view these test flights as critical to mission success, and we're capable of precision flight, and we can replicate trajectories similar to landing on the moon and Mars in ways that you just can't with something like a helicopter, for example. So this gives really good capabilities for reducing risk, and it's a really good way to find issues and fix them while it's low cost and you're not putting your mission at risk. A couple of years ago, we flew another payload for NASA, and that ended up green lighting it for the Mars 2020 mission as part of the Vision system. So that allowed that mission to have a smaller landing ellipse, and they can spend less time driving to the science, and they can get down to work much quicker, as well as land in more interesting areas because they have confidence that they know they can hit their target. And there's the website for NASA Flight Opportunities down below if you want to check out some of the other very, very interesting stuff that they do. Next slide. Another flight campaign I wanted to highlight that we did last year was the Honeybee PlanetVac system. So this is a pretty cool little piece of hardware. You can see it down on the end of our leg there, just descending into the pit of regolith simulant. That's a pneumatic sample collection system. And it flew multiple flights with us, taking off, landing in the sample collection area, taking a sample, and then performing a return flight to mature the system and make sure everything worked as it was designed in a real environment outside of the lab. And pretty cool, they actually ended up collecting more sample here on our vehicle than they did in the lab. So there were definitely differences in how it performed. In this case, it was a benefit to the program. And all of this flight data helped prove the system capability, and it's now on missions to both Earth's moon, but also Mars's moon, Phobos, through the MMX mission. Next slide. Shifting into more of our propulsion tech demo, and all of this technology will flow to the lunar missions as well. But we're really trying to push the boundaries of additive manufacturing, in particular with our 25K broadsword engine, which just finished up a tipping point program through NASA earlier this year. This is a 25,000-pound LOX methane dual expander cycle engine. It was originally started as part of the DARPA XS1 program as a technology demonstrator, and then was funded for continued development by NASA. It's designed to be a boost engine for a reusable small launch vehicle. And also the technology is being applied in some of our smaller engines. So if you haven't heard of the NASA Tipping Point program, it's a great program that helps take technologies and give them a final push from kind of midlife development through commercialization. And the key piece of technology in this engine is its lightweight aluminum thrust chamber, and it's 3 pieces all made from additive manufacturing. And when we built it, this was built on the biggest printer available back in when the program started, which was the EOS M400, and it's pretty exciting. They got new, bigger printers now, so we'll be able to even push the technology further. If you go to the next slide. So this was the final test series of the program, where we successfully demonstrated the new additively manufactured materials we created and built this out of through a 10-second hot fire. Elementum 3D was our additive manufacturing partner on this engine, and they helped us develop new alloys for 3D printing. So these are aluminum metal matrix composites. So we could get improved high temperature strength over kind of the original state of the art, which was ALSI 10 MG, which doesn't have great high temperature performance. So those alloys were used to build this new thrust chamber, and they performed spectacularly. We had some other very interesting advances in the engine. We worked with NUMECA and Oak Ridge National Lab, CFD. That let us do design studies to see how can we use additive manufacturing to improve the performance even further. And then the final testing was done at AFRL Rocket Ridge. Thank them very much for allowing us to test our engine there and being such good hosts. They had superb test infrastructure, so we could get this engine to perform a little better than we could at our Mojave test site. And the picture here is at one of the Apollo F1 test stands, and this engine looks big in our shop, but when you put it next to an F1, it looks really, really tiny. So that was kind of a cool experience. Next slide. Also, propulsion, we've been working for several years on electric pumps for cryogenic propellants. And high power density, low cost, fast assembly and production is what we've been going for. Been working with the turbo machinery experts at NASA Marshall Space Flight Center over several programs, and also with our partner P3 Technologies, to basically take new space innovation and keep the reliability and safety of some of the more mature systems. So to do that, on the left, you can see how we improved our motor performance. We took a space-flown commercial off-the-shelf motor and modified it to improve the performance, so we could get high power density values. We've been able to hit around 15 kilowatts per kilogram, and we're shooting for 20 kilowatts per kilogram power density of the system. So these are really advantageous for small launch vehicles, but also landers. If you go to the next slide. So this is a picture after our successful test for the Artemis program. This was a tech demo as part of the original Artemis studies, and this was to build and demonstrate a liquid methane e-pump last fall. We partnered with P3 Technologies on this for the impeller. It uses our modified COTS motor, and then 3D printed case and impeller to speed along production. The really cool thing about this program was We matured it from design through testing in liquid methane in under 6 months. Really great work by the Masten team, and we were hustling the whole way. Next slide. PermeAM is a technology program we've been working on for the last couple of years. It's started as a NASA SBIR, a Small Business Innovative Research, and it's designed to take the one part of legacy engines that was not able to be 3D printed and make it 3D printed. That's Rigea Mesh, which is a way to create transpiration cooling on injector faces. They take a bunch of stainless steel meshes and compress them together under high temperature and pressure to create a really stiff, really highly flow resistive sheet. And that's been used since the 60s. It's used in the space shuttle main engine. It's used in the RL-10 and a number of others. And it really helps provide good performance to the system. It's unfortunately, though, expensive, because if you're using a coaxial injector element, you need to weld this around every single injector element. And so it limits how you can use additive to create some of these newer injector designs. So we tackled this problem working with Marshall Space Flight Center again, and we were able to create, and Elementum 3D is our 3D printing partner on this. So we were able to create a single piece additively manufactured transpiration cooled rocket engine using variable density micron scale porosity. There's a lot to unpack there, but essentially it was successful, and we demonstrated it in multiple materials, and we're able to tune the pressure drop to the engine settings. This is one of our little workhorse test beds. It's a 100-pound LOX methane test cell. If you go to the next slide. So through this testing, we were able to demonstrate 10x cost saving and 6x schedule saving versus traditional transpiration cooled injector faces. And to prove it out, we demonstrated it in over 25 hot fire tests in both copper and aluminum. We didn't see any low cycle fatigue issues with the porosity, and it demonstrated excellent performance, both on the engine overall, but as well as the component temperatures. Our C-star efficiency was in the 96-97% range. And then the really cool part was we embedded a thermocouple inside the injector face, less than 1/10 of an inch from the hot side. And every single test was showing below 50 degrees Fahrenheit during steady state operations in all of the materials we used. This means that, one is stress. Thermal stress is one of the key drivers in life limitations for rocket engines, and it also is the highest stress component. So if you can keep the injector cool enough, then you can use aluminum instead of superalloys such as Inconel 718, and that allows you to create lighter weight rocket engines without sacrificing performance, and also longer lasting rocket engines, which is a big part of the reusability that we're always pushing for here at Masten. So if you go to the next slide, you can see some of our single element injector test beds on the lower right. And the important part is the discolored portion on the bottom is the porosity section, and that's printed as one piece with the unit. And there you can see some of the copper ones on the build plate. The other nice thing about this technology is it's material agnostic. We've demonstrated it in hot fires of aluminum and copper, and that's a pure copper. And then we've already developed it as well for Inconel 625 and GRCOP 42 as part of the phase 2 of this SBIR. So it's cool technology, and it takes advantage of Elementum 3D's reactive additive manufacturing. It's called RAM, and that allows us to do some pretty interesting things during the printing process and get this porosity into the system in a controlled manner. So we're working on scaling it up right now, and should see some bigger engines later this summer. If you go to the next slide. So we're always trying to push what we can do as far as being affordable and responsive for our customers. And part of that is basically reducing the cost and manpower burden of performing some of these rocket engine tests. And so this is a test cell we put together this spring, going for that affordable and quickly customizable testing. So leveraging the latest technologies. This particular engine is actually predominantly has a plastic chamber out of a high temperature plastic, and then we water cool it to keep it from melting. This is a 600 PSI chamber pressure GOX methane test. And the cool thing about this chamber is we can get very, very quick custom geometries because it's additively manufactured, and it takes about 24 hours to print. So if customers want different sizes, different L stars, different cooling channels, different instrumentation ports, we can turn around a new design and be out on the test stand again the next day. So if you go to the next slide. Another SBIR we finished up this spring in partnership with the University of Central Florida and Made in Space. We were looking at plume cratering and landing pad testing. Understanding how rocket engines create ejecta and craters on landing is important for future Artemis missions in particular, because the Artemis lander could be several times the size of the Apollo lander. And if the engines get bigger and get close to the lunar surface, you can get enough pressure differential there to cause basically something called deep cratering. If you get enough pressure, the plume can start to collimate in the near field near the engine exit, and then it will rapidly excavate in tenths of a second a crater basically down to the length of the entire plume. We have an interesting video on YouTube where you can see some of that in effect based on different nozzle heights. And if that happens, the ejecta can blast basically straight back up into the spacecraft with the force of a shotgun. And so understanding how that happens and how to control it is going to be important to keep the astronauts and the larger landers safe on landing. So the speeds that this ejecta comes back at can be kind of phenomenal. And if you land with a big enough engine, you can actually put the ejecta into lunar orbit. And this little engine that we were testing here, when we were done with this test program, it looked like it got hit with a sandblaster. It was pretty beat up. This was a pretty awesome program. We worked with Dr. Adrian Dove and Dr. Phil Metzger at UCF, and it was just great fun to blast lots of things with rocket engines. Next slide. Another program that we just got picked up for is a NASA NIAC through STMD. And this is a NASA Innovative Advanced Concept program. They view it as the agency's advanced technology program. And this is called FAST, Instant Landing Pads for Artemis Lunar Missions. So what this does is creates landing pads while you're actually landing, so you don't need any pre-placed infrastructure to land your very large lander, and it mitigates the plume ejecta problem that I just showed in the prior slides. So basically, as you come down, as you hover a couple hundred meters above the surface, you can deploy fast, and it creates a pad directly underneath you, and then you can come down and land on it safely. Masten has a lot of experience landing on things, particularly in our Mojave test site. We use a concrete landing pad, and watching how it handles the beat up and abuse of hundreds of rocket landings is really helped us figure out what it would take to create a safe environment on the moon. And the other nice part about this technology is because you don't need pre-placed infrastructure, you can save yourself a preliminary mission, which could cost $100 to $150 million to send robots to the moon, build a landing pad, and then you have to land at a particular location. This would let the astronauts divert to maybe a better landing location, and then you don't need any of that pre-placed infrastructure. So this one is in with Honeybee Robotics and University of Central Florida on this project over the coming year as well. And the next slide is our last one. I just want to say thank you for letting me talk to you today about some of the interesting things we're doing. And with our lunar mission, we're definitely hiring. So please take advantage of all the resume tips you got in the prior presentation and apply online. We can't wait to hear from you. Thank you.
All right, wonderful, Matthew. We do have a few questions. I don't know if you're able to see the list of questions, but I can read you the first one if you like.
Sure, let's do that.
Okay, it says, for Matt, what green hypergol are you using? Can you say?
We use a proprietary blend. It's called MXP351, which doesn't really tell you much on purpose. But that's about all I can say about that.
All right, understood. We have another question here from David Ramirez, which is asking about what is the precision and accuracy of the lander?
So here on Earth, we can land within several centimeters. We've even done tests where we trace the landing gear before takeoff and then see how close we can get to landing in the trace marks on landing. And it's within a couple centimeters when we're really pushing for that accuracy. On the moon, we're still working that out. There's a bunch of different stuff that goes into play there, but we should have a pretty small landing ellipse, and we are using lander vision systems to help us out with that as well.
Wonderful. We have another question here from James Sloan, who's saying, regarding transpiration cooling of the rocket engine, have you heard of any interest in transpiration cooling of re-entry heat shields?
I know SpaceX was looking at that for a while for their Starship before they pivoted to another direction, and it's something we've looked at for some of the hypersonic test vehicles. Definitely, it's potentially quite useful. Yep.
All right, and then we do have, a couple more have popped up here. Question from Yigal Harrell, if I'm pronouncing that correctly. What is the status of the CLPS lander program?
So NASA just gave us the green light about a week ago, and so moving forward as quickly as we can go at this point. We're running quickly towards maturing the lander design and hopefully starting to lay hardware early next year.
All right, and then a follow-up question from the same individual. Which payloads will the lander take with it?
Oh boy, there's a list of 8 NASA payloads that have been published, and I knew I should have had that up from a number of different companies, including Maxar, Astrobotic, some internal NASA payloads, and that is all in the press release. I don't want to list any more lest I forget someone, but we got robotic arms and cameras, and they'll be looking at the spectroscopy of the lunar soil, and a little rover that'll be able to go around and explore some more, and then more to come.
All right, we do have a new question here that just popped up from Trevor. He's asking, what size engine can engine pump drive?
Good question. So the electric pump we showed earlier is sized for about a 5,000 pound thrust rocket engine, and that was sized around, it's basically Rocket Lab size. It's great for both small satellite launch here on Earth. It was, the program originally started as a Mars ascent engine for sample return. So part of the interesting thing they discovered launching from Mars is you don't have a launch tower, the launch infrastructure that you have here on Earth when you're doing a rocket launch. So they really needed the RCS system to come online before the main engine systems that could keep the vehicle stable and steady during the launch phase. The easiest way they found to do it, electric pump. So that's where this originally started. Evolved into more of a satellite boost for third stage. It's also perfectly for kind of like a kick in space.
Excuse me, I have a question about the high temperature plastics for the water cooling chamber. So how high the temperature you can stand?
That plastic can handle about 240 C.
240 C. So another question is why we use a plastic, this kind of material for the water cooling? Is there any advantages to use it?
I used plastic because I wanted to make the engine as cheap and quick to develop in-house as possible. Basically saving money.
Okay, thank you.
Yeah. It's definitely not designed for anything but a ground test stand because it needs water cooling. It's not, plastics really don't react well to cryogenics, so it really wouldn't be a good launch engine, but it makes our lives easier on the ground.
Okay.
All right, so if there are no other questions, Matthew, thank you so much. That was fascinating.
Thank you. Thanks for having me today, and thanks everyone for listening.